Excellent. Well, first of all, I want to say thank you very much for inviting me. It's really a pleasure and an honor for me to be here, and also to have the opportunity to tell you about the research we are doing at EPFL in Switzerland related to wind energy, related in particular to the modeling of wind turbine and wind farm flows, which will be the focus of this presentation. And I will try to, as much as possible, focus also on the work we have done on offshore wind energy. So the motivation of this work, of course, it has already been very nicely presented in the previous talk. And basically is motivated by what we could say is one of the grand challenges of this century, which is achieving energy sustainability. As you know, the current situation is very far from sustainable. The demand for energy keeps increasing at an average annual rate of about 2 to 3% in the world. And at the same time, most of that energy, about 70%, we have seen before, comes from burning fossil fuels, with the, of course, very negative impacts on the environment, air quality, and also on the climate. So it is clear that the energy transition towards more sustainable, more renewable energies has to be accelerated. And among those energies, of course, we can see that wind energy also has been shown that previously that is growing very fast. This is just the total installed capacity in some of the last few years. And interestingly, also, it is supposed to grow even faster if we consider the strategic plans that many countries have for renewable energies, and in particular for wind energy. So one of the main challenges in the design and also the control of wind farms is actually the prediction of their performance. And this in a way should not be too surprising if we consider that these machines are installed in the atmospheric boundary layer, the lowest part of the atmosphere. And we know this is, from a fluid mechanics perspective, this is a very highly turbulent flow, very high Reynolds number flow, which already makes it difficult to predict. But in addition, is what we call a non-canonical flow, meaning that it's not developed normally over perfect, steady and homogeneous conditions. Often is subjected to inhomogeneities and also to the non-stationary forcing due to large-scale atmospheric circulations and forcing. So particularly challenging, actually, is the prediction of what we call the wind turbine wakes. And I think many of you have seen this picture of a very similar one from this wind farm. This is the Hornsrev wind farm. And the conditions were just perfect so that there was condensation behind the turbines, and you could actually visualize the wake flows, which normally we don't see. So basically, these flows are characterized by a reduction of wind speed and an increase in turbulence, which produces reduction in power extraction in the wind farm, and also increase in the fatigue loads in the turbines that are downstream. So just to give you an idea, in this wind farm, which has been studied quite a lot, you can see that in some wind directions, most of the wind turbines actually produce, in some wind direction, the worst case scenario, about 60% of what the first row of turbines will be producing. So the losses can be quite substantial. So as you can imagine, accurate prediction and often fast predictions of these effects are needed for several applications. For example, if we are considering optimizing the layout of wind farms, what is the optimum layout? You have to run many simulations with many wind directions, layouts, etc. So you need very fast predictions. Also, if you want to develop and let's say, even apply as real time control, some mitigation strategies, you need also accurate predictions. For example, this is just one example, will be, which I will show some results later, is what we call active jawing. Basically, is misaligning some of the front row turbines with respect of the incoming wind, which means you are going to lose power. But with that, we can also achieve a deflection of the wakes, which in principle could improve the overall performance of the wind farm. So there is, in terms of modeling, there is a variety of types of models that can be used. And here I classified them a little bit based on the y-axis, the level of representation of the physics, how much of the physics we represent in those models, and on the x-axis, based on the computational cost. So you can see how the simplest models are the so-called analytical models. They are based on the analytical solution of simplified transport equations, where some assumptions have to be made, of course. But the main advantage is, again, that they can provide very fast predictions. Basically, in a matter of a second or a few seconds, you can have a prediction of, for example, the power output in the wind farm I showed you before for a given, let's say, wind direction. On the other side of the spectrum, we have large eddy simulation. Large eddy simulation is a turbulence resolving technique. It's a computational fluid dynamics technique. So it's of course, in principle, it's much more, it captures much more of the physics. It will be much more higher fidelity. But of course, it comes with also high computational cost, and I will be showing you some examples. Let's start with large eddy simulation. In large eddy simulation, basically, again, we solve the conservation equations of mass, momentum, and heat, because heat is very important in the atmosphere. Basically, those equations are filtered using a spatial filter, which is on the size of the resolution that we use. The finest resolution we can use is about a few meters, okay? Let's say about 10 meters or so on that order. So that means that we need to parameterize the effect of the so-called subgrid scale, all the turbulence that is below that scale, which is still quite substantial. Is the so-called subgrid scale stresses, subgrid scale fluxes of heat. And very importantly, also for these simulations, one has to parameterize the effect, the turbine-induced forces on the flow. This is important because at that resolution, obviously, we cannot resolve the details of the boundary layer flow around the blades. So we have to use some sort of model for that. So how is that typically done? There are three main techniques to do that. One will be what we call actuator disk model. I will say is the standard technique, which basically typically makes two assumptions. One is just that normally the thrust force is really the force in the direction of the flow is the important one. And then that the force is uniformly distributed over the rotor disk. Now, the other two, it is based on one-dimensional momentum theory. The other two are based on what we call blade element theory. So basically using the blade characteristics and the forces generated by the blades in two ways. One is what we call rotational actuator disk model. The other one is what we call actuator line. In the rotational actuator disk model, what we find is it's a solution that allows us to obtain a non-uniform distribution of the forces, as you can see here. Here is the forces, unlike here, they are non-uniform. So you can see where the force will be higher and also unsteady, but you don't need to track down the position of the blades. The other one is this one, the actuator line model, where you use the same technique to calculate forces, blade element theory, but the forces are only applied along the lines or around the lines that represent where the blades are located.
Of course, as you can imagine, this is our actuator line model it requires more computational, it requires higher resolution, but also it can capture some of the physics, like for example, tip vortices and so on, that cannot be captured with the other two. Now let me just show you an example of a simulation. The simulation we already did a few years ago. It's a simulation of flow in the atmosphere, which is in this case thermally stratified. There is even what we call a low-level jet. You see, it develops in some places in the world, and can be quite important for wind energy. And its flow through a Vestas 112 wind turbine has a rotor diameter of 112 meters. And basically, let's play it. You can see, how rich dynamics you have with helicoidal tip vortices being shed. Also the hub vortex. You have reduction of velocity in the wave. You have also very clear effect of shear with different advection velocities of the top and the bottom. There is even an effect of veer because there is Coriolis forcing that makes the wake rotate at the same time. So, but of course, these simulations, like any other simulation, is not free from errors. Indeed, one has to be careful, and we need to validate these models. Now, for validation, obviously, one would like to use field data, but the problem is often difficult to obtain data. All the data, the temporal and spatial resolutions that we need at this scale. So it's and also in conditions that can be repeated and cross-check and so on. So basically, wind tunnel experiments offer a very interesting alternative. This is because there you can have full control on all the conditions. You can have full control on the incoming conditions. You can control, you can measure it all in all the positions you want of the wakes. You can reproduce the experiments as many times as you want. You can play with any configurations of the wind turbines, wind farms, and so on. So they are a very nice playground, I will say, for this type of research. So this wind tunnel will have a EPFL. It's what we call an atmospheric boundary layer wind tunnel. It means we try to reproduce a boundary layer flow. That's why it has a long section, 28 meters, and then it has a cross section of 2.6 meters by 2 meters. And it's basically the idea here is our goal is to study our research, or scientific goal, if you want, is to study the interaction between atmospheric, or let's say boundary layer flow in general, and wind turbines and wind farms. As you can see, for example, this is a typical picture of an experiment. So as you can imagine, to do that, you have to use wind turbines that are very small. They are very small. They have to satisfy the geometric scaling of being inside the boundary layer. So basically, we've been working on the design of this type of turbines. This is one of the models we use. This has a rotor diameter of 15 centimeters, and it is designed to knowing that, of course, the Reynolds number at which operates is smaller than large-scale turbines. The blades are designed to achieve an overall performance that will be similar to large-scale turbines. So what we are looking at is what we call kinematic scaling. We try to match the tip speed ratio of the turbine. We try to match as much as possible two very important parameters: the thrust coefficient and the power coefficient. The thrust coefficient, you can see, is about 0.8, which is quite standard value for large-scale wind turbines. This is very important because, in a way, as we will see later with analytical models, it actually dominates, its effect is it dominates the strength of the wake, okay? Is the main parameter in wake modeling. in simple analytical wave modeling, let's say. And the power coefficient is also quite good, with almost 0.4, which is for this size is quite remarkable. So for measurement, we use a variety of techniques. I don't want to go in detail, but okay, a lot of what we do is with laser-based techniques, in particular particle image velocimetry, as you see here, and laser Doppler velocimetry. We use olive foil particles of very small size, about around a micron in size, to see the flow. Let me just show you some sample results. This is from an experiment we did where we were trying to assess, as I mentioned before, this technique of active or strategy of active yawing, which means, okay, if we put 3 wind turbines and let's say the wind comes from left to right, okay, can I play with the angle of this misalign the first and second turbine? The third one we didn't misalign. First and second turbine, what can I do to improve the power? That was the idea. And again, the nice thing of the wind tunnel is in a few minutes, you can actuate the turbines, and of course you have to wait maybe a minute every time to get the converged power. But then you can let's say explore the space of these two angles. And systematically search for the optimum. And we found that the optimum combination, there are two optimum, where more or less you need to use an angle of about 20 degrees in each turbine, and you achieve a percentage of 5% increase in overall power. Of course, the first turbine loses power, and then the second and third increase in the power. What's interesting is that this technique turns out to be even more efficient when when it is used not exactly in full condition, but when it's used in a condition that is slightly off the full condition. Let's say the row of turbines is not perfectly aligned with the wind, but it has the wind, let's say, shifts a few degrees. In that situation, actually, what we find is that, of course, in that case, there is only one side you want to do the yawing. And in that situation, actually, the power increase is about 15%. So you can get much better. It will be optimum for this strategy. For those wind directions, you could activate this strategy. So as I mentioned before, these experiments are very interesting to validate models, and I'll show you a couple of examples. One is for validation of LES. This is more or less what I showed you before, experimental results from the wind tunnel. So what we did is we set up the LES to simulate exactly the same situation, and with the 3 models for the turbines that I showed you before. If you remember, the standard actuator this, the rotation actuator this, and the actuator. Okay, here it's difficult to see to compare the performance, but of course we could select certain transects and look at the performance of the models. You can see here. Okay, so the experiment is in circles, and the models are in the lines. So you can see how, in general, the LES does quite a nice job in general, and we see also that many times we see this is that the models that are based, the modeling of the turbine that is based on blade element theory is normally better in some cases than the standard actuator this model. This is because the actuator this model cannot or does not take into account the non-uniform force distribution, which in some cases can become quite important, for example, in this one.
And let's maybe just move to the other extreme of modeling, the more practical, if you want, or very, very much used in industry, which is analytical modeling. As I mentioned, of course, you need it. Is the only option we have for let's say layout optimization and applications and near real-time control. So basically these models assume a certain shape of what we call the velocity deficit, which is the difference between the velocity in the wake and the incoming flow velocity. This will be the deficit. So whether it's a top hat normally or a Gaussian distribution. There are also some recent models that assume a cosine type of distribution. This approach was pioneered at DTU in Denmark by Jensen, and he assumed a top hat type of shape, and then used mass conservation to predict how that shape will evolve with downstream distance. This was in 1988, quite a few years ago. 20 years later, Franzen also at DTU in a way modified it to account also for momentum conservation. And now, some years ago, we based on the observations we had from the wind tunnel, we saw that the waves were clearly not top hat shape. It was more like actually we could fit nicely a Gaussian distribution. So we proposed, using a similar approach, we proposed a model that is based on a Gaussian self-similar shape, and that has that was based on conservation of mass, or let's say enforces conservation of mass and momentum. You can see all these models are extremely simple. That's why you can, in a fraction of a second, you can calculate, let's say, the wake at any position, the velocity at any position in the wake. And just maybe highlight that all these models require, let's say, some sort of parameter that gives the expansion rate. Let's say you give the shape, but there has to be some sort of expansion. The wave has to be expanding, which is a key parameter. And I will be mentioning it also a little bit later. This is just to show you that, okay, when we use the experiments in black again, wind tunnel experiment, and we try to compare the three models I discussed before, it becomes very obvious that the Gaussian shape is much better able to capture really the shape, the actual shape of the velocity deficit. And again, I want to highlight challenge is how to specify this K growth rate parameter. How does it expand? Okay, and normally this is done assuming a linear expansion with distance. And some measurements point to that. So many measurements taken in wind turbine wakes point that, okay, it's more or less linear. And we'll discuss later how that may actually not be exactly correct, but we will get there. Of course, when you apply these analytical models, that was for one turbine wake. When you want to apply for several turbines, then we need to superimpose them. And recently we worked on methods to do this. One has to be careful because one has to guarantee also that the physical quantities are conserved. For example, we develop a simple method that guarantees conservation of momentum. That is not just linear superposition, is a slightly modified linear superposition. And let's get maybe to see how this applied in actual wind farms. And for that, I think it's best to just go to this Hornsrev wind farm of the picture. And this is a simulation, a large simulation showing the flow at half height, instantaneous flow at half height in this wind farm. It has 80 wind turbines. And you can see the rich dynamics. Okay, it's obvious that you see the turbulence in the incoming flow interacting with the wakes clearly interacting with the downstream turbines. The meandering of the wakes, this is very important phenomenon, especially for understanding loads on turbines, and also for the recovery of the wakes themselves. And then the flow in the wake of the farm itself. You see how the reduced velocity is felt at some distance from the Now, just to point out that this simulation, this full simulation, to have a simulation like this, it takes about 1,000 CPU hours. So I think we used 100 processors for 10 hours, just to give you an idea of the computational cost. And here what we did is we were interested in understanding what the effect of wind direction on the wind farm power, let's say, on the wakes, of course, and how they affect the wind farm power. So you can see here, I'll be running an animation where this actually what you see here is an average field, and this comes from one LES, all right? This comes from one LES that comes in this direction, the wind corresponds to this direction. You see there is a 40% loss in power, about 60% of the power being produced with respect to, let's say, this wind turbine, okay? And then what I'm gonna do is I'm gonna be changing, I'm gonna plotting results from other of the 92 simulations when I change the angle, okay? So I change the angle, the power increases because the wakes don't hit directly the next turbine, so I have very long distance to recover. But there are local minima here where you see it hits this row, even though the distance of turbines is much larger than this. And again, we will reach this direction, which is the one I showed you before, where again, you will dip again to about 60%, and so on, and then it will recover. But pay attention how you need a very little change, about 6 degrees change in wind direction or 7 degrees, and you go from worst case scenario, full wake condition, to, let's say, almost the maximum power you get in the farm. So this is interesting also because small change in wind direction, you will have to manage at the level of the grid and so on. It can give you, in a very big wind farm, can give you quite a large fluctuation in the power output. And then just to connect again to an analytical models, the obvious exercise we also did is, okay, let's apply the analytical model to see if it reproduces this, okay? And the circles is the LES that I showed you before. The blue is the analytical model without any modification. For now, don't pay attention to the red, it's just the blue. So we can see that it does a decent job at following the trend and the results. Sometimes it over-predicts systematically, especially in these relatively long distances, and I will discuss later why I think it is. And then what we did also is we say, okay, let's now just do an optimization exercise, and for that, we need to, because there are so many simulations, we need to apply just the analytical model. So it will be just the analytical model with join, allowing for join of the turbines and running tens of thousands of cases to try to find an optimum strategy for join. And that will be the red line. Okay, so you see, you may say, okay, you don't improve so much. Well, okay. When you look at the power gain, you will see that a little bit like before, when you're a little bit off, like 3 degrees or so from the full wake, you actually get the maximum benefit, which is about 15%, like before. Interestingly, in this kind of situation, which is different from the tunnel, we found that at full wake condition, it was better not to actually do active join. So yes, I hope that gives you an idea of how we can play with these different types of models and how they complement each other. Sometimes the LES, because it's so much higher fidelity, we can use it to improve analytical model. Now, of course, your center, RECO, is on offshore wind, and I think it's a fantastic initiative, and it's extremely timely initiative. Because offshore wind energy is growing very fast, and is expected to grow very fast. For example, the European scenario, which is the one I am more familiar with through projects and so on. Basically, in Europe, especially in the North Sea region, there are big plans for offshore expansion. Because again, this avoids all the problems that come from installing wind farms in highly populated countries like the Netherlands or Denmark or so on. So basically, you can see, for example, in this map, this is just an illustration. You can find maps like this, many more maps like this. But the basic idea is that there are many wind farms that are being planned, and there are but that brings new concerns. That brings new concerns because basically what happens is that people are realizing with some of the offshore wind farms, even the ones already installed, not to mention the ones that will be installed, which will have a much higher density, that there is an effect of some wind farms on other wind farms. So we have the farm wake effect, these farm wakes that can extend tens of kilometers and can be then affecting the next wind farms. It's even becoming a bit of a legal issue, and even at the level of border between countries, because there are no clear legislations on that. So it's a very active kind of field, and field with a lot of interest. So basically, we were interested on understanding, okay, how do these wind farm wakes behave, and can we use our tools to study them? And basically, I'm just going to show you a study that we really, we are just finishing. It's still in progress. Well, we just finished it, actually. We just submitted it. But it's really, really in progress. It's a study where we did basically 16 LES simulations to study the wind farm flow in particular, but also the flow inside the wind farm, because there are quite interesting effects. And what we did is we did combinations of 4 different sizes of wind farms with 9 rows, 18, 27, and 36 rows. And we used 2 different densities. 7 rotor diameters, that will be the typical density, for example, of the Honsref wind farm. And we use also 5 rotor diameter distance. And then we applied 2 configurations. You can think of it also as 2 wind directions, okay, if you want, more or less, in the Honsref scenario. The fully aligned, and then something like staggered, that will effectively distance between turbines affecting each other increases. So just some results. This is inside the farm, at the end of the farm, and these are the wakes. So you can see that for any given configuration and density, you will see that clearly there is a clear effect on the number of rows. And as you increase the size of the farm, the decrease in the velocity in the wake of the farm, up to these are 10 kilometers, it's stronger. Okay. Interestingly, of course, you can reach a size. This is 36 rows. This is extremely large. I don't know if there is any wind farm. I don't think there's any wind farm that large yet, but that you will reach something that is kind of almost, asymptotic behavior of what you will have if your wind farm will be infinite, and then you will cut it, and then you have a farm wake. That's an interesting also observation.
But also just to point out that, for example, if you go from a line to stagger loses also more velocity in the wake. And also there is an effect, of course, on the density. Okay, the higher the density, the more reduction, which makes sense. And of course, it was also for us very interesting to study if the analytical models I showed you before, will they be able to predict this? Because that will be quite useful, again, for planning purposes. And what we did is we put 4 of these models to the test, including ours. And what we find is that, okay, some do better than others, but there was some systematic kind of overestimation of what happens in a few kilometers down the farm. So of course, this could have implications on you may be underestimating the negative effects of these wakes if you use these models, okay? So interestingly, also for some configurations, let's say stagger, which will represent, if you want in Honref, a relatively long distance between turbines. This is what I pointed to being a little bit over-predicting. In those situations, the models also, they tend to over-predict with respect to the LES, which is in black. We hypothesized that all these effects could actually be related to the basic assumption of the linear growth of the wakes. So, and this is something we've been working recently, because what happens is that linear assumption of the wake is normally based on relatively short distances. Okay, the people say, okay, maybe I have measurements from, let's say, 3 rotor diameters to 10, normally maximum, something like that. And then they do a fit, and more or less it looks linear. But what happens is when you look at longer distances, we start to see that linearity, let's say if you take this linear trend, it will not hold. It will start to decrease the growth rate. Okay, so we have recently, I don't want to go much in detail, but we recently developed a method that is physics-based, and actually it borrows on ideas using analogy to Taylor's scalar dispersion theory, which is, if any of you have done air pollution, this is used in air pollution to model what we call the Gaussian plume. It's a Gaussian plume model. It uses a Gaussian distribution which expands. The plume expands. And the solution to that, interestingly, it satisfies that the plume, and again, our solution for wind turbines, following the analogy, of course, they are not exactly the same, but we use a bit that analogy. They will expand linearly for relatively short distance, let's say up to 8, 10 rotors, something like that. And then smoothly it will transition towards scaling of the distance to the power 1/2, square root of the distance. And so we have applied, this has already been published, and we have just applied that to this situation. And we find that effectively this makes actually a big difference. And you see this was our previous model assuming linearity. This is the one that assumes that uses this nonlinear growth rate. And you can see how the prediction or the overestimation is reduced. Of course, not perfect, but is substantially reduced. And also even the prediction of the power in those cases of staggered wind farms, it can also improve. In aligned cases, it doesn't make much difference though. So I just want to maybe just finish mentioning that, okay, some of all other activities we have in our lab at EPFL involve field measurements. I'm a very fan also of going to the field and measuring the real turbine wakes.
And what we do is we use these so-called scanning Doppler wind lidars. So basically, they are laser-based instruments. You shoot basically you shoot a laser beam, and it uses the Doppler effect with the aerosol particles in the air, and it is able to measure along the laser beam the wind speed, the component of the wind speed in that direction along the laser beam at a spatial resolution of 18 meters and a temporal resolution of 1.3 seconds. So it's quite powerful. Every second and a little bit more, you get up to about 2 kilometers. You get a measurement point every 18 meters. Of course, only one component, though. But to, let's say, maximize its use for turbine wakes, we have this strategy of having two of these instruments you see in this video. This is the first one, looking forward. The other one is the one looking backward. This one looking backward is where we plot here. It's actually scanning the wake. It could be volumetric, but normally we do just two-dimensional scanning, horizontal scan, which is what you see here. And what you see here is that radial, let's say, component of the velocity in this wake. When we do very fast scan, we can actually it's a bit approximated, but we can create an animation of how the wake behaves. And you see it's very nice up to 1 kilometer. You see clearly the velocity reduction. You see the meandering of the wake that I also showed in the LES. So this is quite interesting data that then can be used for understanding this flow. And just to also finish, maybe just mention that, of course, when we put these instruments, we let them there for several months, actually, normally. And so we capture many different types of conditions, so we can systematically try to understand, for example, what is the effect of atmospheric stability. We just isolate the effect of atmospheric stability. For example, these cases, this is a case, the first case on the left. By the way, this is the mean velocity. Okay, so this is in red is larger reduction. This is the deficit, actually, so it's larger reduction. And this is the increase in turbulence. This is the turbulence intensity. This is the level of turbulence, if you want, which increases, as I mentioned, due to in the wakes. But you can see here, it's quite interesting because in cases that were at night, where the boundary layer was thermally stratified, and they were characterized by low turbulence level. We were having turbulence level as low as 2.2%, which is extremely low. The wakes go on for very long distances, which is very important, of course, when you have a wind farm, because that means that the next turbine, which may be located around maybe a 6 rotor diameter, will be here. Is going to have a much larger losses than I showed you for Hornsref before. In more or less neutral cases, it will be more standard. And then, let's say, in higher turbulence, let's say convective conditions, you will have wakes that are actually, because the ambient turbulence, again, related to also contaminant transport, it helps the mixing and the entrainment of fresh air from around. It makes the wakes recover much faster. So this is actually quite useful, beneficial effect, if you want. So with this, I think I will finish, but I just want to maybe point out, last night I just wrote a couple of points just for closing, because, okay, I think there are a lot of open questions that need research. I think it's a research field that is growing very fast and is very exciting. So I just point out to some of them, and I think, for example, from the analytical modeling side, there is a lot of work to be done to for example, something that is very important is to extend this kind of modeling, simple modeling, fast calculation type of modeling, also to turbulence quantities, because okay, now we can predict the power losses quite well, I think, and we're making a lot of progress, but there is not a lot on the turbulence level that is needed, for example, for also fatigue loss and to understand how much turbulence is inside the farm. All the models at the moment are highly empirical, or most of them are highly empirical or semi-empirical, so there is quite a lot of room there. There is also a lot of room in analytical models to account for example, non-stationarity effects when the conditions are not stationary. The models, I assume, they only work for stationarity at the moment. So non-stationarity, when you have non-homogeneity, for example, pressure gradients, when you have topography that makes that the flow is non-homogeneous, even being in the wake of another turbine is non-homogeneous, right? Blockage effects, thermal stability effects, and so on. I also think it's important to have more research on numerical frameworks that cover the full spectrum of the scales I showed you earlier in the presentation. You know, from large atmospheric scales, let's say mesoscales, to let's say turbine blade scale. The coupling of these models is very important, both with let's say CFD, but also with analytical models, again, for having something relatively fast. The fact I mentioned topography, atmospheric stability, wind farm interactions I already kind of discussed, but there's a lot of room there. Also, the turbine design, innovative turbine designs, is something that we always use the same design, and I think there is a lot of room, and I'm quite fan of the work of Professor Ogia on the wind lens technology, and I think this kind of new ideas can bring really bring fresh new perspective and possibly major breakthroughs. Also, innovative control strategies. We have to find ways to control and let's say control the wind farm as a whole, not just turbine by turbine. And of course, I think there is a lot of starts to be a lot of attention, and there will be a lot more in the coming years on floating wind turbine technology, because to go offshore, as we discussed, is a very interesting option. So, for example, something we started to look at is some sort is what is the effect of the motion, because there's going to be a motion of the turbines, right, when you put a floating turbine. Interestingly, this motion is very similar to what we call dynamic dynamic control of dynamic yawing, for example, and or dynamic downregulation. What it means is it is introducing an unsteady oscillation in the wakes, which interestingly it can be very, very beneficial for wake effects. So that's something we are starting to explore, and I think there is a lot of potential there. And anyway, I will just finish here, and I just want to say I think your new center for offshore wind energy is extremely well positioned. I am very aware of all the excellent work done by the different groups there. Of course, I know best Professor Ogia, Professor Uchida from the numerical modeling side as well. But I've seen a lot of very interesting work also coming from the structural side, from the floating turbine technology, and so on. And I'm looking forward to discussing more with you. So thank you very much for your attention.